So here's my version of the depth first search algorithm. Mine goes down and then right, left, and up. And here you can see that the bottom two nodes kind of get sent back to the start very quickly within the search. And that's because of the way that my algorithm is set up and for the given maze. So this maze here, you can see that the top two nodes, since they go down first, go down all the way towards the bottom, close to the two bottom nodes. And then from there, after that, they kind of create a wall around them so that they could no longer search the upper parts of the maze. So this makes my algorithm a lot slower than the one that was included in the framework because it's really just two nodes traversing the whole maze for the rest of the remaining time. I kind of talk about this in my report, and I discuss the run times and the comparison between the framework's runtime and mine. I'd like to bring up some of the packet loss that I saw during the DFS and some of the random search algorithms. So here you can see that two of the nodes are traveling on top of each other, searching through the maze. And I believe that this comes from the fact that the two meet at a junction together. And in the strategy code, the send and receive are done right before the nodes move. And since they're so close together and they're moving almost simultaneously, when they send the packets, they go straight to receiving, and it might not give them enough time to receive the packets that they sent to each other. So they never know that both of them are taking the same path into the throughout the maze. So they're not ever building a wall around each other or noting that the path that they are on has already been visited because it's happening at the same time. So I think that by adding a delay after sending packets, this would allow the receiving end to fully fill their buffer from the three other nodes, and it would not cause them to overlap each other in the maze. So another algorithm that I implemented was the random search one, and at any junction it would generate a random number, and the number would correspond to a direction. So then the node would then go in that direction. And this is different from depth first search because it doesn't prioritize a direction over another. It just depends on whichever random number is chosen. I also wanted to note that the nodes know they're at a junction based on a series of if statements where I did every combination of a possible 2, 3, or 4 junction. I don't think that there are any maps on the list that have a junction of 3 or 4, but in that case, this algorithm could definitely be applied to maps that do have that number of junctions. So a little more on how the UDP communication works. If you go to the strategy file under the go method, you'll see that each node will first send data and then receive data in a buffer from the three other nodes. The sent data is the x and y coordinate of each node so that the other nodes know exactly where each node is on the map. And then also it sends out data on the surroundings, so whether up, down, left, or right is a wall or not. And in the received data in the buffer, it processes each packet one at a time. And by processing the data one at a time, it's able to piece together a wall around itself formed by the solved maze of the other three nodes. And this breaks it down so that it solves a smaller portion of the maze. So they each have 4 segments of the maze that they solve at the same time. And this proves to be a lot more efficient than solving it with 1 or 2 nodes, since they're all attacking separate parts of the maze at once.